Let's look at an example of a certain type of bacteria, the Lactobacillus acidophilus, and bacteria, and that helps us digest milk in our intestines. Now, the colony of Lactobacillus bacteria obeys the law of uninhibited growth. So that means they can continue to grow, and one particular colony is modeled by the function, the following function, n of t 1000 e to the 0.009242t, where n of t is the number of bacteria after t minutes. So the first question here is find the initial amount of bacteria. Now that is still the same as we had right from the beginning that we started this term. The number in the front is always the initial amount, and so in this case we would call it n sub 0, that is 1000. Now the reason for that is that we can say that n of 0 equals 1000 e to the 0.009242 t, that means times 0, e to the 0 is 1, so that is exactly 1000. Now, our continuous rate of growth of these bacteria is the number in the exponent in front of the t, that is our k. So we're just reading it off here, and that's just how we defined our continuous rate of growth. So that is 0.009242. Now, the next question is, what is the size of the population after 10 minutes? So t is in minutes, that means t in this case is 10. T equals 10. And so we need to find n of 10. So n when t is 10. And so we just plug in 10 for our t. And then if we plug that into the calculator, so all these kind of questions will be on the calculator portion on the test, for instance, because else there's nothing else you can do now by hand, and you wouldn't know how many bacteria you actually have. And so when we plug that into the calculator, we will get 96.7 bacteria, and we can say after 10 minutes the population is approximately 1097 bacteria. So they've grown by 97 in those 10 minutes. Now, then the next question will be, how long will it take the population to double? So that's a very common question. We are oftentimes interested in what either to reach a specific value or to double, find the doubling time if it's growth, or to find the half time if it's decay. So what does that mean? Well, when we had 1000, we could say, well, when does it become 2000? Let's try that. So let's say, so 2 times 1000 is 2000. So we want to know for which, so at which time will the population have grown to 2000 bacteria, so doubled. So we have to solve for t, which is an exponent, so that's, now you see why we have been doing everything we've been doing until now. In order to get to the exponent, we need logarithms. But before that, we need to have our exponential expression entirely on its own. That means we need to get rid of the 1000. So I'm going to divide both sides by 1000. And so we get 2 on the side, and on the right side we get 0.009242 t. And let's take a moment to think about what just happened. We doubled the amount, put it on the left side, but then we had our amount on the right side and divided by it. So we ended up with 2. If we had had our amount be 500, our original amount of bacteria, then the doubling would have been 1000. If we divide it by 500, we'd also end up with 2. So all we really need is the 2 there, because we could have said, well, we had 1 bacteria and now we have 2. It will take the same amount of time to double no matter with what amount you start. And that is the kind of the nature of the exponential growth function or decay function, same thing, as we will see later on. So here now we can say that our exponent is the same as our ln because we have a base e. And then at the very end we simply divide by the factor in front of the t. So we get ln of 2 divided by our continuous growth factor. Now when we type that in to our calculator, we will get the following. So our answer is 75. Now what does that mean? That means that after 75 minutes the population has doubled. Now, remember that we said a few minutes ago that it doesn't matter where we start. Every time we double, it will take 75 minutes. So if we start at 1, it takes 75 minutes to double to 2. It takes 75 minutes to double to 4, and so on and so forth. So every time, if you have 1,000, now it takes 75 minutes to get to 2,000. Again, that's the power of the exponential function, that we continue to, like, no matter how big the number is, every time it doubles or every time it grows by a certain factor, it takes the same length. That's why suddenly the growth becomes so steep, because if you take 1,000,000, it takes 75 minutes to double to 2,000,000. And that is one of the interesting parts also about exponential growth of people on Earth, right? Because we started off with a certain amount and we keep doubling, so following an exponential growth pattern, and we keep doubling every so often, every so many years, and eventually that becomes a problem, and it has. So that's kind of what the background is. This kind of problem is what's in the background and how this all operates.